Hi everyone. Today I'll be talking about our work on efficient approximation of fractional hypertree width. This is joint work with Viktoriia Korchemna, Daniel Lokshtanov, Saket Saurabh, and Jie Xue. Okay, start by introducing tree decompositions. So the tree width of a graph is a measure of how tree-like a graph is. So a tree decomposition is an arrangement of the vertices of a graph in a tree-like structure satisfying some properties. And tree decompositions are really helpful for designing algorithms for graph optimization problems. And typically, the algorithms look like a dynamic programming style algorithm on top of the tree decomposition, right? Okay, so what are the properties that we want satisfied? So now the tree decomposition is an arrangement of the vertices in a tree-like structure. So the vertices of the tree will refer to them as bags. So for example, here for this graph shown here, the below is a tree decomposition. So every vertex of the tree contains a subset of vertices of the graph. And the properties is that every edge of the graph is contained in some bag of the tree decomposition, right? So for example, the edge BC is contained in this first yellow bag BC. And for every vertex V, the bags containing the vertex form a connected subtree. And here, for example, B, the vertex B is contained in these three yellow bags, which form a connected subtree here. Okay. And how do we measure how good a tree decomposition is? So the width of the decomposition is size of the largest bag minus 1. So the width of the decomposition shown here would be 3 minus 2, which is, sorry, 3 minus 1, which is 2. And tree width is just the width of the best decomposition. And tree width equals to 1 if and only if the graph is a forest. All right. Exactly the properties you don't need to know too much for the sake of this. Okay, cool. Now we need the notion of hypertree decomposition. So that is tree decompositions for hypergraphs. Common hypergraph width parameters are three of them. So one is fractional hypertree width, second is generalized hypertree width, and third is hypertree width. The naming can be a little bit confusing, generalized versus hypertree width. I'll get into the specifics later. For defining these three notions, we require the definition of edge cover and fractional edge cover. So what is an edge cover of a hypergraph? So the edge cover of a hypergraph is a subset of edges such that every vertex is covered by at least one edge. So in this given example, the gray edges form an edge cover of the hypergraph because every vertex is contained in one of the gray edges. And a fractional edge cover is a weight assignment to the edges such that every vertex is covered by a total weight of at least one. So for the same graph, if we assign half to each of these edges, then you can see that for every vertex, the sum of the edges containing, sum of weight of the edges containing these vertices is at least one. And therefore, this is a fractional edge cover. And the weight of this fractional edge cover is just 1.5, right? And one can observe that a fractional edge cover is never more than the edge cover. And in fact, fractional edge cover can be computed in polynomial time by using an LP. Okay. So we can go into defining fractional hypertree decompositions now. So fractional hypertree decompositions are tree decompositions for hypergraphs. But you can imagine that you can construct an auxiliary graph, which is called the Greifman graph for the hypergraph. So you can add an edge between every pair of vertices that are contained in a same hyper edge. Then this graph is called the Greifman graph. Then your fractional hypertree tree decomposition is just the tree decomposition of the Greifman graph. But another way to look at it is also that again, your vertices are arranged in a tree-like structure. And if U and V are contained in a same hyperedge, then there is a bag containing both of them. And for every vertex V, the same rule, right? The bags containing V form a connected subtree. But the difference between tree decomposition and fractional hypertree decompositions are mainly in the width of the bag, right? So we saw that tree width is the number of vertices minus 1. But here, the width is measured by the fractional edge cover of the bag, right? So instead of measuring the number of vertices, we measure the fractional edge cover of the bag. And fractional hypertree width is just width of the best decomposition. So why is this notion more useful than tree decompositions for hypergraphs? So imagine your hypergraph is an entire, there's only one edge in your hypergraph, and that edge spans all the vertices in your hypergraph, right? Then your tree width is going to be very large. It's going to be n-1, but your hypertree width is going to be much less, right? So it's just going to be 1. And that's what you would expect. Just one bad edge should not increase your width measure by a lot. Okay, and what is generalized hypertree width? It's the same, it's very similar notion to fractional hypertree width, but now the measure differs as it's not measured by fractional edge cover, but rather it's just measured by the integral edge cover or edge cover of the bag. And now the width of the best decomposition using this measure is called generalized hypertree width. Generalized is confusing because there's another notion called hypertree width, which has no relation to generalizing tree width. Okay, so the notion in literature is just confusing. Okay, so what are hypertree decomposition? So this notion of hypertree width was introduced by George Gottlob, Nicola Leon, and Francisco Sarcallo. It was in fact introduced in the database context because these decompositions are very helpful in for databases and CSPs, for mainly for query evaluation in databases. It turns out that generalized hypertree width is NP hard to compute even for constant width, and therefore this notion of hypertree width with additional extra conditions was introduced, and it turns out that they're easier to compute. So hypertree width has an extra condition on the edge cover of the bag that makes it easier to compute, right? So now when you're measuring the width of the bag, you're just not looking at all possible edge covers, but you're looking at edge covers with a specific condition, right? With a special extra condition. And this condition is just that when you are looking at the edge cover, they can only contain vertices from the bag among all the vertices in the subtree rooted at the bag. It's not necessary for us to go into the condition, so I'll just leave it at that. But just know that there exists an extra condition. Okay. And it turns out that hypertree width is at most 3 times generalized hypertree width. So it's in fact useful in practice, and that's why it was introduced. Now, we are ready to relate all the hypergraph parameters. So fractional hypertree width is at most generalized hypertree width, which is at most hypertree width, and which is at most 3 times generalized hypertree width, which is at most log n time fractional hypertree width, right? So all the width parameters are at most like log n times away from fractional hypertree width, right? So in our work, we are approximating fractional hypertree width, but because of this relation, we actually can approximate generalized hypertree width and hypertree width too. Okay. Before we move on to our results, we'll go into a quick history of what is known for all these parameters. So in 1981, Mihalis Yannakakis gave a linear time recognition for generalized hypertree width equal to 1, which are the class of acyclic hypergraphs. And it's been known since 80s, I think, so that it's generalized hypertree width and fractional hypertree width are NP hard even for omega greater than equal to 4. But George Gottlob, Matthias Lanzinger, Reinhard Pichler, and Igor Rasgon show that it's NP hard to check whether generalized hypertree width and fractional hypertree width are at most omega, even for omega greater than equal to 2, right? So even for 2 in 2021. And George Gottlob, Nicola Leon, and Francisco Sarcallo, in the paper that introduced hypertree width, gave an XP algorithm for hypertree width at most omega. So this directly gives an XP algorithm for constant factor approximating generalized hypertree width. Because recall that generalized hypertree width is at most 3 times generalized hypertree width, right? Okay. And in 2010 SODA, Daniel Marks gave an XP time order omega squared approximation. So he gave an n plus m to the omega cubed time omega squared approximation for fractional hypertree with at most omega. Okay. And these are all like positive results. Like we saw some algorithmic results. So one might ask, okay, how best can you approximate? Are these the best possible results? And it turns out that for hypertree width and generalized hypertree width, they're at least as hard as set cover. both to compute exactly and approximately. And because of that, we have a pretty strong hardness of approximation. So basically, assuming hardness of set cover from the 2019 result for set cover, assuming ETH, there's no f of omega n to the little o of omega time g of w approximation for hypertree width and generalized hypertree width. So this rules out FPT approximation for hypertree width and generalized hypertree width, and it's even stronger, right? So it's an f of omega n to the omega time FPT approximation. That's ruled out. Okay, but what about fractional hypertree width? So fractional hypertree width is at least as hard to approximate a tree width. And assuming small set expansion hypothesis, no constant factor approximation for tree width can be done in polynomial time. And this also rules out a constant factor approximation in polynomial time for fractional hypertree width. And this is from the 2014 result of Yu Wu, Per Austrian, Tonian Pitasi, and David Liu. Okay, and very recently, Matthias Lanzinger and Igor Razgon gave an FPT approximation for generalized hypertree width for graphs of bounded intersection, right? So here eta is the bound on the intersection of hypergraphs in the hyper edges in the hypergraph. And they gave an f of omega comma eta time omega into omega plus eta approximation, right? So an FPT approximation in FPT time. And it turns out that hypergraphs with small bounded intersection are common in practice, and that's why there's motivation to study this special graph class. Okay. With that, one might ask, are hypertree decompositions really helpful? It turns out yes. They're very useful for constraint satisfaction problems, solving database conjunctive queries, combinatorial auctions, and many more applications. In fact, if one were to search the term hypertree decompositions in Google Scholar, all the articles that are reported in the beginning are from the database or like AI community, in fact. And that's because it's been studied a lot from this point of view because of their application. Okay. Cool. Before going into our results, I'd like to give an example of how hypergraphs can be used in CSP solving. So many natural problems can be expressed as CSPs, which are constraint satisfaction problems. And what are CSPs? They're just a conjunction of clauses that need to be satisfied. A CSP instance is given by describing some variables, domain of variables, and constraints on the variables. And many problems can be modeled as a CSP. So for example, tree coloring can be modeled as the CSP, right? But how do we construct hypergraphs for CSPs? So now we have these clauses, right? So for every vertex in your CSP, we have a vertex, for every variable in your CSP, you have a vertex in the hypergraph. And for every clause or constraint, we add a hyperedge, right? So now we have a hypergraph. And now what one can do is we can find a hypertree decomposition for this hypergraph. And then we can solve CSPs using some form of dynamic programming. Okay. With that, let's head on to our main result. So our main result is a truly polynomial time. So it's like n plus m to the order 1. So that note that the exponent is order 1 and not order omega. It doesn't depend on the fractional hypertree width. So it's a truly polynomial time log n log omega approximation for fractional hypertree width. And if you recall, we know that hypertree width and generalized hypertree width are at most log n away from fractional hypertree width. So this directly gives a truly polynomial time log square n log omega approximation for the other width parameters. So hypertree width and generalized hypertree width. And we also obtain an XP algorithm. So n to the omega poly m time log squared omega approximation for fractional hypertree width. And along the way, we also have a new version of Menger's theorem, which is the Click-Menger's theorem. We'll look at what the theorem is later. But in fact, our result, I told you that here there was like a log n factor, right? But in fact, for special graph classes, this log n factor can be improved based on if the graph has bounded independence number or the degeneracy of the bipartite incidence graph of the hyper graph, and also like the maximum size of intersection of two hyper edges. So for like, if you look at special graph classes based on these parameters, then it turns out that our approximation is actually better. So let me quickly highlight our results. So ours is the first truly polynomial time algorithm for fractional hypertree. So prior to our work, all approximations used like xp time, so n to the omega time at least. And we give a polynomial time, like truly polynomial time, FPT approximation for fractional hypertree width and generalized hypertree width on the class of bounded intersection graphs, right? So earlier I told you this result of Lanzinger and Rasgon, the 2024 result. So our ratio is comparable to theirs. We get an omega into omega plus eta time approximation up to polyn log, like log eta log omega factor. Their approximation ratio and our approximation ratio are nearly the same, but the main difference is that theirs runs in FPT time in omega and eta, but ours is a truly polynomial time approximation. And the second is that ours substantially improves over the previous best known approximation by Daniel Marks, both in terms of the approximation ratio and the running time. So if you look here, Daniel Marks gave an approximation ratio of omega squared. We improve it to log squared omega. And the running time, we improve from n to the omega cube to n to the omega. Okay. And let's quickly look at the techniques that we use for our results. So our results go through the general framework of Robertson symbols for computing tree width. This was even used in the previous work by Daniel Marks. And we use a Leighton-Rao style rounding for finding balanced separators that are fractionally covered by few clicks, right? And this is just like the Leighton-Rao style rounding means that the ball growing argument of Leighton-Rao. And the ideas of combining this Robertson inverse framework and Leighton-Rao style rounding actually stems from this log-n approximation for tree width by Bodlander et al. So we make this kind of combining Robertson inverse and Leighton-Rao work for fractional hypertree width, right? Okay, and I also told you that along the way we have this new Click-Menges theorem, which is our main ingredient. Let's look at what this Click-Menges theorem is. So if here we are given a graph G on n vertices and two subsets A and B, subsets of vertices of the graph, and also a set of clicks in G. And then we show that there exists an AB separator, which can be covered by a few clicks, or there exists a collection of paths such that no clicks in F intersect at least some many paths, right? Log n many paths. Here you can see that there is like a log n factor between the cover and the paths. And we can show that, in fact, this log n factor is essential. Okay. With that, let me mention our main open problem. So our open problem is that, does there exist an FPT approximation for fractional hypertree width? That is, does there exist an F of omega time approximation in G of omega time for fractional hypertree width? And another thing is, can we use our new Click-Menges theorem for other problems, right? So our new Click-Menges theorem has already found use for even whole free graphs, for something for even whole free graphs, and it'll be nice to find uses for it in other problems. Thank you. And I'd like to thank Daniel Marks for some of the lovely slides on 3D compositions in CSPs. Thank you.